This episode will compare qualities and characteristics of gas-atomized and ultrasonically atomized powders. Right now in the screen you can see two SEM images. On the left you can observe typical gas-atomized TA64. On the right part of the slide you can see ultrasonically atomized TA6 powder. The very same composition, completely different powders. You can observe that there are plenty of satellites on the left, while particles on the right are completely smooth and satellite-free. That is a general characteristic of ultrasonically assisted atomization. As there is no high-velocity gas in ultrasonically assisted methods, there is no way for the particles to collide and create satellites. That's why we're always observing smooth and satellite-free spheres. The other quality that you can observe is particle size distribution. Let's take a look at the particle size distribution diagram. In gas atomization, there is much broader particle size distribution, both fine and oversized particles. So the cut for specific AM or powder metallurgy methods is limited. In ultrasonic atomization, we can fine-tune the frequency to fit into specific needs. Higher the frequency, smaller the particles are. For example, in case of heavy alloys, we can get around 80 to 100 micro with 20 kHz, while we can get below 40 micrometer at 60 kHz ultrasonic frequency. Shifting the frequency of ultrasounds can get us highest yield possible within the fraction required for the processing. Different powder metallurgy and additive manufacturing methods requires different particle size distribution. For example, electron beam melting usually uses coarser particles. 45 to 106, 140 micrometers, those are used basically to prevent so-called smoke effect. On the other hand, LPBF, laser powder bed fusion, requires finer particles to create a smooth surface quality as it takes and to create very fine lattice structures. With ultrasonic atomization, we can fit for one or the other method, changing the frequency of ultrasounds. In gas atomization, we need to cut the final product with sieving, and then the yield is somehow limited. Let's take a look on the single particle from both methods. In gas atomization, you can observe multiple defects. It is possible that such particle will be decorated with satellites, it could be porous, it could be deformed. In case of ultrasonically assisted methods, it is very hard to get anything else than a perfect sphere. In our book of powders, we have dozens of different examples, starting from magnesium until refractory materials such as Rhenium. All of those perfectly spherical. This Sphericity is a very trademark of ultrasonically assisted methods. Let's take a look on the cross-section of the powder. One of the typical defects in gas-atomized materials is so-called gas porosity. The particle itself is like a shell. So inside the particle you have a bulb of a gas that was used initially for spraying. Such gas porosity can be later on passed to the material, for example, in DED processing. It is much harder to get dense material with porous powder than with powder that is bulk. Not having compressed gas as a spraying medium in ultrasonic method, there is no way of introducing gas porosity there. Another topic are cooling rates in both methods. Gas atomization usually provides very high cooling rate, providing very fine microstructure. In case of ultrasonically assisted methods, cooling rate is lower, usually around order of magnitude lower than in gas atomization. It is still possible to get fine microstructure or metallic glasses there, but in some cases the dendrites are coarser or microstructure is not as fine as in gas-atomized materials. The last topic is oxidation. In gas atomization, plenty of gas is used, so even smallest contamination can be introduced into the final powder. ppm level of oxygen and nitrogen are introduced afterwards into the melt. In case of rePOWDER, ultrasonic atomizer, there is only a bit of gas present in the single time in the chamber. Even more, it is possible to use so-called getter to melt a tiny bit of titanium or zirconium to scrap all of the leftovers from the inert atmosphere. If we're processing melting such a titanium piece before atomization, it is basically gathering all of the contaminants from the atmosphere and providing the highest possible quality of inert gas. It is also possible to have another in-situ reactions. We have a few examples where we used reactive gases such as carbon dioxide or nitrogen as a spray gas into an ultrasonically assisted method. To wrap it up, using rePOWDER, it is much easier to get high quality powder with tailored particle size distribution than in gas atomization. The process nature is much more consistent compared to gas atomization. There is no chaotic supersonic flow of gas, only a gentle mist of liquid titanium and other materials that we are willing to atomize. Controlling such a mist is much easier than controlling power washer of liquid steel as in gas atomizer. Thank you so very much for listening. In the next episode, we'll explain how to utilize rePOWDER for alloy prototyping, starting from arc melting until final atomization of refractory powders.